Okay, lecture 12. So we have only 2 remaining lectures before our midterm examination. Okay. You have the third homework. So we have studied the Poisson equation in our previous lecture. So I just prepared a very simple homework problem to exercise the solution of a Poisson equation. So think about these two material systems. One is material 1 having epsilon is given by epsilon 1, and consider another one called as material 2 and whose epsilon is epsilon 2, and the interface is located at x equal to 0. So x equal to 0. So in negative coordinate, here we have material 1, and for positive coordinate we have material 2. So you can easily understand this is the case we can frequently see in the realistic problem. So for example, having one material and another material, and they have different permittivity. That is quite frequently occurring in our course. So my question is, now they have, in general, they have different permittivities. So here it has epsilon 1 and epsilon 2. Typical case is, for example, this one have certain numbers, however its number shown in the material 2 is somewhat different from the one for the material 1. So this is quite normal, so please think about this case. Although this is not the real homework problem in today's lecture, sorry, today our pencil works a little bit strangely, so I have to switch to the eraser. Anyway, so although this is not your final homework, but please think about this simple case. Say you have material 1 and you have material 2, and at the boundary shown here, and the boundary is here denoted as x equal to minus t1. Here t sub 1 means that just thickness of your material 1, and let's say that its thickness, the thickness of material 2 layer is given as t sub 2, and x equal to t sub 2 is presenting or representing the right boundary of this system. Let's say that at these 2 points we have the given potential written as phi 1 and phi 2. So although our homework problem assume the existence of a certain charged layer at certain position, but for while, so when your first solution procedure, please neglect this charge layer. Just to consider our material 1 and material 2 are completely neutral, and just to try to solve your Poisson equation for this simple system without any charge. Then what happens? So although you must solve the equation like this, second derivative of your potential is equal to the law. However, in this case, of course, when we have homogeneous permittivity, permittivity is uniform, then we can write down in this way. However, in my simple problem, so not the realistic homework, but our homework like 2.5, in this case we assume that everywhere inside this system rho the net charge density equal to 0. It means that although we must solve a Poisson equation, but actually in this case we are allowed it just to solve a Laplace equation. Please try to solve this problem. You know, this problem is quite easy because you know we have just vanishing second order derivative, and it just follows the forms like ax plus b, a linear function of the real space position. So what you have to do is, okay, for this region and another region, inside it you can assume that phi equal to given as a sub 1 x plus b sub 1. A and b are unknown parameters, however they are assigned to each region, so you can write down this way, and also you can write down a sub 2 x plus b sub 2. So you immediately understand when you take the second derivative of this function, the second derivative goes away, and also this one goes away. Now you understand they are really the solutions of a Laplace equation. And what you have to do also is when x equal to minus t sub 1, then your potential should be phi sub 1. What is the other condition you have to apply? When you have x equal to t sub 2, the right boundary point, your potential should be phi sub 2. So please try to match your values a sub 1, b sub 1, these kind of things to match this a sub n, a sub 1 and b sub 1, a sub 2, b sub 2. We have 4 different numbers, a1, b1, a2, b2, and by supplying these two boundary conditions at t minus t sub 1 and t sub 2, we supply just two conditions, and we need 2 more. Where can you find 2 more conditions to set these parameters? Of course, we must concentrate on this interface. Please try to impose the continuity of your potential itself. When x equal to 0, then your potential should be continuous. Otherwise, you have just high electric field at the interface. That is not allowed it. So you have to have the continuous of your electrostatic potential. But still, you need 1 more. What is the remaining 1 more condition? The remaining 1 more condition is just continuity of your displacement vector. So your displacement vector calculated in the first region 1, material 1, and the displacement calculated in your second material 2, should be the same, because you know this is the boundary condition applied at the material interface between material 1 and material 2. So by applying these 4 conditions, you can calculate a1, b1, a2, b2 as a function of the applied bias voltage phi sub 1 and phi sub 2 and other material quantities t sub 1 or something like that. So please try to solve this preliminary problem. Once you solve this preliminary problem, homework 2.5, then now you can go to the realistic one named as or numbered as homework number 3. Now, in this system, in this preliminary one, I did not consider any kind of charge state inside it. However, now I'm asking you, please consider another charge state that in somewhere here the location is given as x is x t sub naught. So well, anyway, yeah, the position is given as t sub naught, and in this t sub naught position you have a certain very shallow sheet charge. So please understand what is it. Here you have n sub naught, and this n sub naught is just a number of electrons per unit area. And what is it? Here you have another one. You have here delta. In this course, I sometimes use this delta symbol to show you very short distance. However, in this case, this delta is not an infinitesimally small length scale, but it is a function called as Dirac delta function. So you know this Dirac delta function have a certain property. For example, let's consider this one. So centered at t sub 0, and when we integrate this Dirac delta function from minus infinity to the positive infinity, then it should be 1. But so it's not that interesting, but point is if your integration area or integration domain is quite close to t sub 0, or I should be more careful, if your integration domain includes this t sub 0, then it always gives you the integration result 1. For example, if I say so, then it will give you number 1. However, if our integration does not include this t sub 0, then it gives you just number 0. So let me just do it together with you. For example, let's consider this case. Your integration is performed from t naught plus 1 to t naught plus 2. Obviously, this integration interval does not include t sub naught. So let's say that this is x, and there is a t sub naught, and here we have a t sub naught, and our integration interval just starts from 1 away from t sub naught, and here we have another one, t sub naught plus 1, t sub naught plus 2. If we make integration only over this interval does not include the t sub naught, then it gives you just number 0. So simply speaking, this Dirac delta function just detect where your integration contains the center of this Dirac function or not. So let me just come back to our original case here. Now you can understand this one. So when you have a look at the density we are assuming here, once again this n sub naught having the unit of number per square centimeter, and this Dirac delta function gives you just number 1 without any unit when you make an integration over the length scale. So what should be the unit of this Dirac delta function? It should be also per centimeter scale. When it is per centimeter scale and when it is integrated over certain length scale, then this centimeter and dx cancels out in terms of their unit, then gives you just unitless quantity number 1. So simply speaking, when you have a look at this number, then still, although it looks a little bit weird, but this one gives you just a density, volume density number per cubic centimeter. So now let me give you more concrete example. So now say that your n sub naught is given as 10 to the 12 per square centimeter, and let's say that your n sub naught, this sheet charge density, is just located under 1 nanometer. So within 1 nanometer you have certain charges, and when it is integrated over 1 nanometer, it gives you just number 10 to the 12. So let me just do it. I mean that if you have the volume density like 10 to the 19 per cubic centimeter, and if it is located just in a distance of 1 nanometer, then what it gives to us is since we have just 1 nanometer, 1 nanometer is given as 10 to the minus 7 centimeter. This is just 1 nanometer, and it will give us 10 to the 12 per square centimeter. Simply speaking, there we have a little different idea about its shape. So we don't know whether that is actually concentrated on 1 nanometer length scale, or for example even shorter one like 0.1 nanometer length scale. We have a little idea. If we have the distance like 0.1 nanometer, then what happens? We have to introduce density, volume density 10 to the 20, and we have to have 10 to the minus 8. Still we have 10 to the 12. I mean that we wanted to keep the integration result. So we wanted to keep this area, but if we introduce short distance, then what we have to do in order to keep this same integration value, then we must introduce a little bit higher function. And if we reduce once again the integration domain, or in other words, if our function is highly localized in a short distance, then we have to introduce much higher function value. So we wanted to keep this procedure infinitely. It means that we are reducing the depth or the width of our integration further and further, and following this reduction of the depth, then the height of our function should go to the infinity. Of course, keeping the integration result as the same value, and eventually you will get certain function like this. If we have x, and if that is centered at t sub naught, then we have a very tall function. How tall is it? Infinitely tall. And it is very narrow function. How narrow is it? It is infinitely narrow. However, the area for integrating this narrow and tall rectangle gives you just number 1. That is the Dirac delta function. So let me just come back. I hope that most of you already heard about Dirac delta function in somewhere in your coursework, but if you don't understand this one, then please try to understand. So simply speaking, I'm not doing any trick on this density. We are talking about three-dimensional density specification, and I wanted to say that by specifying n sub naught times Dirac delta function, I mean that this way. There are charges. They are highly concentrated at x equal to t sub naught. There is a highly concentrated one, and although we have no idea about their exact function shape, but when it is integrated, now it's 2D density is n sub naught. This is the meaning of the terms like n sub naught times Dirac delta function centered at t sub naught. So now, sometimes in the modeling of semiconductor device, you sometimes see this situation. I mean that your electron can be sometimes regarded as just sheet charge, although that is located somewhere, but it is more convenient to consider its not three-dimensional density but two-dimensional density. So when it has this two-dimensional density, and if it is really highly localized, then we can treat it as just a sheet charge, and it is given as here. So this axis, along this x-axis, it is highly concentrated, and for other two dimensions, yes, this one gives us just a two-dimensional density. So are you with me? So please note that n sub naught is 2D density, not 3D density. So, well, this is the end of my description about homework number 3. So first, before introducing this sheet charge density, first try to solve your system without sheet charge. After that, now you have sufficient information about your system. After that, please introduce your sheet charge to somewhere. So then you can. Actually, let me just give you the final word. Here, you have net charge density given as here. Therefore, it is contributing to your law, the net charge density. And when you make integration of rho, then if your integration area contains x equal to t sub naught, then it will simply give you something like q times minus q times n sub naught. If your integration does not include the point x equal to t sub naught, then it will give you just number 0. This is quite obvious. Yes, so maybe in this course you can see only two types of charge distribution. One is uniform distribution. I mean that here we are considering quite highly localized charge density, but another case, the case we are frequently looking at is, for example, you may see certain charge density shown here. It is just a constant over our material number 2. So this one is uniform charge, and this one is just sheet charge. So you are now looking at the case of sheet charge density. Okay, this is your homework number 3. So if you have any question on this problem, then please let me know. Okay, so now in the previous lecture we have spent quite a long time on the continuity equation, so I hope that all of you understand now the concept of continuity. Continuity equation is just counting number of particles. So it just consider that if we wanted to estimate the time dependent number of particles inside this small box, it is related with incoming flux of that given particles. If we are counting the number of electrons, then we must consider the incoming flux of our electrons. So what is the flux of our electron? That is typically written as F sub n in this work, and that is actually given as minus 1 over q times j sub n. What is this? This is our electron current density. So simply speaking, the continuity equation makes some relation between the time dependent change of our electron density, that is written as lambda n over lambda t, and another incoming flux that is related with electron current density. That's the reason why our continuity equation just looks like this. So I explain once again. So here minus sign is introduced because this divergence just goes the divergence of a certain particle flux. So it is outgoing or escaping flux. So the reason why we introduce a negative sign is we want to convert it to convert into incoming flux. And at the end of our previous lecture, we need additional terms. Okay, our original continuity equation just stated that the only way to change the number of particle is just movement of a charge or movement of a particle through the boundary of that region. However, if we include also some cases where particles are generated or particles are annihilated, then we can introduce this generation term or the opposite term. So maybe you can ask me this question: electrons are elementary particles, so we cannot demolish it. So how can we generate electron in our continuity equation? It is not possible. Yes, you are right. Electrons are elementary particles, so we cannot generate electron or annihilate it. However, please note that what is the electron we are talking about? We are not talking about the electron occupying our valence band. When we say electron in this sense, this means that just electron is in the conduction band. So, so say that now we have this situation. Here we have a conduction band minimum and valence band maximum, and if we have one electron in this position, then we say that, oh, we have one electron. However, if our electron is transit from one point to the other point, in this case, now we don't have any electron in this conduction band, then although the number of electron is still number 1 for this entire system, but only for conduction band, then what happens? Previously we had one electron, but it's suddenly disappear. So it looks like an electron is annihilated. However, it is never gone away. It is just change its K position. But since our observation or description only considering the electrons in this energy range or this band, so we are now saying that electrons are gone and number of electron is reduced. So please note that there is no actual demolition of our electron. So from this description, it is clear like this. Although we say that one electron is removed, but actually this is not a single event. So I mean that here, in order to have this R sub n recombination of electron, then we have to have some case like this. Then what will happen? So from the viewpoint of our conduction band, we will say that, oh, we lost one electron. One electron was gone. And previously there was an empty space and we called it as holes. However, if one electron is moving from conduction band to the valence band, then eventually it will occupy one of its empty state, and the number of empty states is reduced by 1. So we say that also holes are, the number of holes is reduced by 1. So in this case, we say that both of electrons and holes, their number are reduced, and it looks like some negatively charged particles and positively charged particle, electrons or holes, are meet together and they are annihilated. But please, this is not the case. So they are just there. The reason why we call it as a recombination is just the observation point or observation range of our description is just limited for conduction band and valence band. The total number of electrons is always conserved. So this phenomena called as recombination. So let's think about this one. From today, Korea try to make stop the trade with other countries. So at the same time, it says that total amount of Korean won is now fixed. So every day, actually, the Central Bank of Korea always publishes some money. So therefore, the total number of Korean won is ever increasing. However, now it is stopped, and I give you 1,000 Korean won, 1,000 Korean won, and 1,000 Korean won. What will happen? Then the amount of money I have is reduced by certain amount. However, the total number of Korean won is still kept, because although we are exchanging our money, but this is just inside the same system. Quite similarly, conduction band and valence band exchange their electrons. To each of them, it is a huge event. However, from the viewpoint of the entire silicon system, it is just a movement of one electron from one position to the other position. The entire quantity is just kept. So are you with me? But now think about this case. Except for this one, let's assume certain island, and for this island, let's say that in order to give any money to the other one, it is not allowed to direct handover of my pocket money to somebody. Let's think about this one. In reality, we can do it, direct handover of my money to you. However, it is not allowed it, and always we must send it to somewhere. After that, this somewhere send it to another position. I mean that let's assume that there should be an agent between two persons. So, I have money, I need money, but direct transition, handover, it's not allowed by law. For example, always we must introduce a certain agency, sometimes called as a bank or something like that. Then what will happen? So I send my 1,000 Korean won, and what will happen? After that, the bank will send it to another guy. So please think about the time required for this entire system. If we are doing this job one to one, then the transition, the money transfer is immediate. So when I give it to him, then my money is immediately reduced. However, if we have the things called as a bank, then think about this one. When I give it to bank, first there occurs minus 1,000 and increase of 1,000. And how about this guy? From the viewpoint of this guy, so do you have any increase of your pocket money? No, although professor promised me to send money, but he didn't give me any one, so I have 0. after that, only bank make money transfer to this guy, recipient, then eventually it will become 1000 and money in the bank will be just 0. Why I'm talking about this very not that interesting story to you? So now we are considering conduction band and valence band, and up to now we have talked about direct electron transition or electron exchange between conduction band and valence band. However, unfortunately, in the case of silicon, the direct exchange of electrons between conduction band and valence band, that is not allowed. Why that is not allowed? Because due to their band structure. So the more probable way we can exchange our electrons between conduction band and valence band is to assume the existence of the intermediate agent in my example. So conduction band send their electron to this intermediate state called as trap. Then this trap takes the electron. After some time later, it sends it to valence band. So now you can understand, after long time has passed, then you can see that, oh, conduction band lost its electrons and valence band obtained some electrons. However, if we are just to make a snapshot of a number of electrons, then internally the number of electrons stored in this agent state trap level is slightly increased. After that, it is reduced once again to its original level. So are you all with me? So now we have to consider the existence of trap level, and when we have a certain trap level, then what will be the form of this generation and recombination expressions. So that was this kind of modeling job has been done by 3 persons, Shockley, Reed, Hall. So actually they did the job, and this is independently done by also another guy, so they are called as a SRH. So it is the name of 3 authors. So although I have no time to derive entire procedure, so if you are interested, you are really strongly recommended to refer your reference books, because understanding this SRH is very important when you are serious about the modeling of semiconductor device. But anyway, I think that right now the most important one is to understand this physical picture. So simply speaking, the transition or exchange between conduction band and valence band is not direct, it is indirect. And for this indirect electron exchange, we have to introduce this trap level. And how can you generate this trap level? It is quite simple, because when your crystal has a certain imperfection, then it will introduce some electronic states in the forbidden zone. So this is a forbidden zone. Then they are working as trap levels. So maybe you remember that we have talked about Professor J's quite famous diagram. So I don't remember the exact time we discussed, but here we have EC and EV, and if we introduce good N-type dopants, then we have certain levels like this, and if we introduce good P-type dopants, then we have levels quite close to V. But at the time, I told you that if we introduce certain impurities whose energy levels are located in between, for example, this case, they are treated as very bad guys in our electronic application. The reason is now clear. If the state is quite close to this conduction band, then what will happen? Even in this case, your state can capture your electron. However, what will happen? Since it is so close, it will so frequently exchange its electron. So the number of electrons is not altered because this time scale is so short. Then for this guy, interaction with valence band is almost impossible because this is just orders of several milli-electron volt. So energetic distance between valence band and this N-type dopant state is just close to 1.0 electron volt and even higher. So since energy is too much different, so it is almost impossible for electron occupied in this state go to that way. This is not allowed. So simply speaking, although in general, every state in this forbidden zone can interact with conduction band and valence band in principle. However, if that is too close to conduction band, then it is solely determined by only conduction band. And if it is too close to the valence band, and it is just interacting only with the conduction valence band. The one which is actually being used as the so-called recombination center is always the energy range in between. For these guys, it can interact with conduction band. At the same time, it can interact with the valence band. So that's the reason why the deep level state. What is the deep? Here, deep means that the distance from conduction band is quite high, and distance from the valence band is also quite high. In this case, we call it as deep state. And for this deep state, it can act as a recombination center, and when you have this recombination center, then that is critically bad for your electronic operation. So you don't want to introduce this kind of materials, impurities into your system, because that will kill your device. So although you make certain device, but it behaves quite badly. Why? Because your sample contains a lot of impurities, deep level impurities. So you want to minimize use of those impurities. Okay. So now, if we have sufficient time, then we have to start the derivation of a SRH recombination model. However, unfortunately, we are not that much prepared. So I just directly introduce you the final form of SRH recombination expression. So now we can consider this one. So Rn minus Gn. So it means that please note that this is not Gn minus Rn. So actually Rn minus Gn. So if it has a positive sign, what does it mean? It means that Rn is dominant. What is Rn? The recombination of our electron density, the reduction of our electron density. So if this value is positive, then our electron density will decrease, and if it is negative, then we will have a net generation of electron density. So please have a look at the final form shown in this A5.16. So as you can see, it looks quite complicated, but most important one is here you have terms like this: NP minus Ni square. So please, first of all, at equilibrium, what will happen? If you have equilibrium condition, then you know the product between electron density and hole density equal to square of intrinsic density. So from that rule, you can see that at equilibrium, the net generation or net recombination becomes just 0. At equilibrium case, this one doesn't make any sense. Then now let's consider non-equilibrium case. In this non-equilibrium case, there is no guarantee that NP equal to Ni squared. So if these two values are the same, then we can have some values. But please think about this one. So initially, at a certain system, it was at equilibrium. So everywhere, the product between N and P was equal to Ni squared. Yes. Then from this left boundary, let's assume that we just inject some electrons into this system. So for a while, for some time, for a short time, for this area, electron density is somewhat higher than in its equilibrium value. Now let's consider the sign of our net recombination. So previously at equilibrium, let's call it as NEQ and PEQ was equal to Ni squared. But now intentionally electron density was increased, and now electron density is given as equilibrium density and another one, injected one. So now injected electron density and hole density is equal to the previous one. Then what is the inequality? Which one is larger? Obviously, you now understand NP product is larger than Ni squared. Then what happens? The sign of this NP minus Ni squared becomes a positive number. Then as I told you before, positive number over this net recombination simply states that electrons are recombined and its density is decreasing. What is it? If you inject electron into your system and if you have tons of excessive electron, then it is recombined with your whole system, whole gas. Then eventually the number will be decreased and relaxed to its equilibrium case. But now think about the opposite case. By some way, by some way, your NP product is almost close to 0. Now let's consider this case. Then what will happen? If this one becomes quite small, then now we can neglect this NP product compared with Ni square. Then you can see that this one goes away and only we have minus Ni square term, and net recombination becomes negative value. What is it? It means that we have net generation of electrons. So if we have such a case, then now we can expect electrons are generated from certain position. Then of course it will move away by some action, but anyway we can consider net generation or net recombination depending on its local state. So now we have another thing to be discussed in this slide. Here in this lower part you can see very unfamiliar things like please name the new things in this expression. Tau p, what is it? You never seen it before. Of course you know n, electron density. However, n1, have you seen it before? So no. And tau sub n, you never seen it. And also p sub n. So their physical meanings should be found following your derivation procedure. So that's the reason why I strongly recommend you to visit the library or some website. Then you can read through the derivation procedure of this SRH model. Anyway, what I wanted to say is consider a n-type sample. So this n-type sample, then what happens? And in the case of an n-type sample, of course electron density would be much higher than hole density. So in the case of an n-type sample, then we can safely neglect these quantities. Although more or less tau p and tau n, they are comparable. However, since n is much higher than p, so we can neglect this case. Then what happens in this case? Now you have some approximate form like tau n and 1. And now here you have NP product minus Ni square. But let's just say that now we are considering net recombination cases. So simply speaking, I'm assuming that so NP product is much higher than square of Ni, intrinsic carrier density. Now we have some excessive carriers in this case. Then what will happen? Here we have n times p. Then what happens? Then if we have these two quantities n and n plus n1, n1 is typically for n-type sample. n1 is also very small number compared with this n value. So then the remaining thing is p over tau p. So simply speaking, if we have some excessive charges in our system, for example, in the case of an n-type example we are considering, let's say that hole density is somewhat increased from its equilibrium value to equilibrium value plus some injected value. Then it means that the reduction or relaxation of this excessive hole density is simply given by this 1/tau ratio. So if you have some excessive holes inside the n-type sample, then it will recombine, and its time constant is given as tau sub p. So actually the reason why we call it as tau sub p is obtained from this physical consideration. So of course, since we have here the other one, we have neglected it in the case of n-type sample. However, in the case of a p-type sample, what happened? P-type sample, actually electronic contribution will goes away, and for p-type sample, then it can be considered as injected electron density has certain relaxation ratio following the relaxation time of tau sub n. So of course tau sub n, tau sub p, they have a similar rate, and depending on the state of our or cleanness of our sample, this tau can vary quite a lot. So if you have a very good sample, then it can be, for example, microsecond or even shorter. And if you have quite if you have a good sample, then this tau can be quite long, like a millisecond. However, if your sample contains a lot of impurities, then it can reduce quite significantly, like a microsecond and even shorter. Then please think about the dependence of your tau and doping density. If you have high doping density, then this tau will become quite short. And if you have almost no doping density, then tau will become quite high. Because the physical origin of all of this mass is the trap. And trap is actually just the state generated from unwanted impurities. So if you have more impurities, then you can have this kind of thing. Okay, so although our discussion for SRH is relatively short, and I just show you the final answer, final expression without delivering the derivation procedure, but please try to self-study this derivation procedure, because it contains a lot of details about the modeling of this state. And one more thing is, when you working as an engineer in this semiconductor field, first of all, you must concentrate their own state, the increasing the current, the maximum current level. That is your first priority when you have just the initial production. However, eventually, when you want to commercialize your device into the real field, then more important property is not your on state property. Actually, the off state property of your device is far much more important. Then who decided this off state property? Actually, this guy. This all kinds of imperfection inside the silicon or any kind of material really determines the amount of off-state current. So therefore, if you are serious about this electronics, then you should really serious about studying this topic. So sometimes people say that, oh, this device can conduct a lot of current. Yes, having high performance current or large current is not that difficult if you really concentrate on only that aspect. But point is, we must introduce a balanced device which shows high performance at the same time showing reasonable off-state performance. That is quite important. I want to stress this point again and again. Please, therefore, when you study these semiconductor devices, all of dirty things and difficult things and important things, they are related with those kind of imperfection. So clear, crystalline, everything just looks clean and sounds good, but this is just a first step. So for your real device, you must address all kinds of difficult problems. Okay, now let me just summarize our long discussion about equations and something like that, and we are now ready to enter into the device. This is the full set of equations we will consider in this course. This equation, the full set of equation, has its own nickname called as drift diffusion model. The reason why we call it as drift diffusion is simply because in this case we consider our particle current density, electron current density, as a sum of drift and diffusion. So we have this kind of description. Hole density, also hole current density, also have two same one. So here we have drift related one, diffusion related one, drift and diffusion. That's it. That is just the reason why we call it as drift diffusion model. And other equations are common for different models. Every model, every semiconductor device model should solve Poisson equation. Well, I will not solve the Poisson equation. If you say so, you miss something. Poisson equation, since we are talking about the movement of charged particles, every time you should consider Poisson equation. Or somebody say that, oh, I will not solve continuity equation. No, because it is related with the movement of electrons and holes, so you have to consider continuity equation. Up to this point, everything is so clear, but beyond that point, that is a matter of your choice. Depending on the degree or complexity of your problems, sometimes you can rely on relatively simple form of current density, or sometimes you must use more difficult form or elaborated form of current density. But anyway, for this course, I think that it is just enough to use this drift diffusion model. If we need a more advanced model, then we will introduce it whenever it is required. Okay, so I think that this is the last slide before PN junction. Here we have the PN junction, and the last slide is related with dielectric relaxation time. So this dielectric relaxation time related with the time of our majority carrier. I mean that previously here we have talked about this one. So let me just write down more clear way. In this SRH description, we have considered this way. In an N-type sample, there are so many electrons and not that many holes. But if we introduce additional hole density, then what will happen to this additional excessive hole density? That follows the time constant of tau sub p. So it is because why it is following this tau sub p should be understood. So let's say that this is EC and EV, and here we have real space. Position wise we can have different values of EC and EV, but right now I just drawn a homogeneous one. And now let's say that here we have additional holes by some way. Now here we have additional holes. Wow. Then what happens? How can we relax this uncomfortable situation to more comfortable situation called as equilibrium? Then the best way would be movement of these holes toward left side or right side, and there we can see the contacts. Okay, there are contacts, and eventually these holes are reach at contacts, then it is consumed by that metal, then escape from our system of interest. But you know that takes time. How long does it take? How long does it? Because this is just movement of holes, so there is no other particle. It should travel, for example, half of your entire sample length. After that, it will go away. If we do not consider any kind of recombination, then this movement will be the only way we remove these excessive holes. However, in the case of the existence of a SRH center, then we can say that okay, so these holes can be recombined because there are so many electrons, and some of those electrons are moved this way, eventually kill these excessive holes. So it is much better way or quicker way, faster way to remove excessive holes. However, that was all related with N-type sample. But now assume that instead of this N-type sample, now we have a P-type sample. There are tons of holes in this system. There were, and now we introduce even additional holes in this system. Then what will happen? Now situation is a little bit different, because when this minority carrier will just occur, yes, this is a minority carrier. After that, it should move, and eventually they should go away. However, in the case of this majority carrier case, there are so many same species, so by using this one, we can easily eliminate this, simply speaking, excessive majority carriers can be easily relaxed. So that is the point. In the case of simply speaking, there are different mechanisms just movement of particle and recombination. Which one is dominant is determined by which one is faster. In the case of a minority carrier, actually transport of this minority carrier from one injection point to the contact will take almost forever. So therefore, we are relying on this recombination. However, in the case of a majority carrier, we have much faster reaction of our majority carriers, because majority carriers can be injected from our terminals quite quickly, and we have so many similar carriers nearby. So compared with this SRH recombination, this one transport becomes much quicker. So let me just have a look at. So sorry about that. Okay, so this is the last slide. I have prepared our discussion on dielectric relaxation time. Please read, and if you have any question, then please send me an email, or you can directly come to me and make some discussion. So now let's call it a day, and from the lecture 13 we will start the discussion about the PM junction. Thank you.